So today we are going to talk about a generalization of Green's theorem, which is known as Stokes theorem. So first let us recall what is Green's theorem. So the theorem was that suppose I have functions m, n defined on a region D, okay, and let us say delta D, this denotes the boundary of D, with positive direction. This positive direction just means that I orient the boundary in such a way that the area region D is on the left hand side of myself. That is, if this whole thing is my region D, and if I want to keep the region left, I have to give this boundary, this direction. With this direction, this thing is called delta D, that is the boundary, and the inside region is D. Now if I have further conditions on m and n such that m, n and the partial derivatives del n del x, del m del y, these are continuous, then Green's theorem tells us that double integral over D, okay, del n del x minus del m del y dx dy, this is integral over delta D m dx plus n dy, where the right hand side denotes the line integral of the vector field f, which I can write as mi plus nj, then this is nothing but integral over delta D f dot ds. Okay, this is the usual line integral. So from a double integral we are coming down to a low dimensional integral, that is a line integral. That is what is the essence of Green's theorem. So that way it generalizes the second fundamental theorem of calculus that we have already seen. Now today what I want to do is can actually be explained by the following picture. So what we have done in Green's theorem is something like this. So these are my axes, this is x, this is y, this is z, okay, and this, let us say, is my region. So this is outside boundary is delta D, inside thing is D, and then I had given a function whose double integral over D comes down as line integral of some other function on delta D. Now the question is, what are we going to do if I am in a situation as the following? Let us draw the picture again. So this is x axis, this is y axis, this is z axis. Now notice that the region D which I have drawn in the picture 1, that is lying in the xy plane. But suppose this region D is not lying in the xy plane. Suppose it is in some oblique region like this. Okay, suppose this is my D. It makes sense to talk about delta D again. But in that case, what can we do? Is there any analog of Green's theorem in this kind of situation? In picture 1, I know what to do. Question is about picture 2. That means D is not on the xy plane, it is on some oblique plane. Then what do we do? Now to understand that, we need a restatement of Green's theorem, usually known as the vector form of Green's theorem. Well, it is just as follows. Consider the function f, which is, as I said before, mi plus nj. Okay. Then I say Green's theorem states the following. This is called the vector form. So what is the vector form? It is given as double integral over D curl f dot k dx dy, this k stands for vector, that is equals to integral over delta d f dot ds. Now for those who do not know the formal definition of curl f, first let me say that. So f is defined on the region D to R2, so it is a vector field. I know already the definition of f of xy, that is mxy comma nxy. I can write it in this form or equivalently in this form also, mxy I plus nxyj. Okay. Then what does curl f stand for? Well, curl f means just value of this determinant I del x m j del y n then k del z 0. Okay. It is also formally written as grad cross f. Okay. This symbol, this inverted big delta, when we say this dot f, we mean gradient of f, and then f has to be scalar valued, which produces a vector field. But here in this case, grad cross f formally means this determinant ijk del x del y del z, and then the components of the function, the x component, the y component and the z component. So if I calculate this, what does it come to? Let us see. Del y of 0 is anyway 0. Now I have to look at del z of n, but n is a function of x and y, so del z of n is 0. So I get 0 dot I, that is the first quantity. Then I look at j, then I have to apply del z on m, okay, and then 0 on del x. Okay. Now del z on m is again 0 because m is a function of x and y, it is independent of z, so that quantity is 0, so is del x of 0. So I get 0 dot j. Now what remains is k, so that component I will write. That turns out to be clearly from the formula of determinants del n del x minus del m del y k. So curl f is actually the vector del n del x minus del m del y k. So this is a particular case of the definition of curl of f, but anyway let us continue with this particular case, then I will come to the general definition later. Now then what is curl f dot k? This turns out to be just del n del x minus del m del y. Okay. Now if I want to use Green's theorem, the left hand side of Green's theorem is double integral over d del n del x minus del m del y dx dy. So that can be written as double integral over d curl f dot k dx dy. And then by Green's theorem, the right hand side is f dot ds. This is what I said, the alternative vector form of Green's theorem. Now in general, given a function f from R3 to R3, it will be then of the form f of x, y, z, that is equals to, let us say, p x, y, z, I plus q, x, y, z, j plus r, x, y, z, k. In that case, curl f stands for this vector field I del x p j del y q k del z r. This is called curl f. So now we know the general definition of curl. Now, how do we generalize this theorem of Green to Stokes is actually given by generalizing the vector form of Green's theorem. So we look at the vector form of Green's theorem and try to see where exactly we are using the fact that my region is on xy. And then we try to generalize it for arbitrary surfaces. So Stokes theorem, what it will do is that you have given a function and a surface, a very special kind of surface, not arbitrary surfaces, which is bounded. Let us say the boundary of the surface is a simple closed curve. Then the surface integral of some function is connected to the line integral of the function over the boundary. That is what the Stokes theorem says. So when the surface is actually in the xy plane, then Stokes theorem actually reduces to Green's theorem. So that way it's a generalization. Now how do we generalize? So again we draw the picture. These are my axes. This is my D. Boundary is delta D. Now when we look at the statement of Green's theorem, there is some k which is coming. I am talking about the vector form of Green's theorem. Okay. So it is curl f dot k. What exactly k has to do with this surface? That's what we want to understand. Now it's very simple. If you look at the normal to this surface in this direction, this is k. This is the k direction, right? Now in the general situation, this is x, this is y, this is z. Suppose I have a very simple surface like this. This is D, the same D, but this time it is not on the xy plane. I am putting it some oblique position. Then who should play the role of k? Well, the answer is natural, that you look at the normal to the surface n, which goes in this outside direction. That n is going to play the role of k. And the other thing which you have to be worried about is about this meaning of this outward normal. Okay. Now, intuitively, given any surface, let me try to draw a surface like this. Suppose this is a surface, and this disk portion which I have written is the boundary of the surface. Now, when I am talking about this kind of a surface, I can certainly see that this surface has two sides. One is outside, other is inside. Okay. Now, what is outside and what is inside, that can vary from person to person. Okay. Well, I call the outside direction is this. Okay. That is what I am going to assume. So, given any surface which has this kind of phenomena, that is, it has two sides, I can talk about the outward unit normal vector. And we can actually derive the formulas of outward unit normal vectors also. Now the only trouble is, which is bit counterintuitive, but it can happen, that there exist surfaces which may not have two sides. Okay, it might happen that the surface has only one side. Now mathematically to determine how do you exactly express side of a surface is a bit complicated. So we will try to understand in an intuitive fashion what exactly is a side of a surface. For example, given this surface, suppose I want to paint one side of the surface. Okay, so I can start painting one side of the surface and can finish it. Then the other side of the surface, there is no paint there. That is certainly true for this surface. It is like a hat actually. So you can always paint the outside of a hat, or you can paint the inside of a hat, or if you like, suppose you have two colors, red and blue. You use the red color on the outside of the hat and the blue color on the inside of the hat. That is possible. But there are surfaces for which it is not possible. So one such surface I will draw for you. It's called Mobius strip. It's a very interesting surface because of the following reason. Okay, and then do you understand what exactly I mean on this surface? So suppose you have a band of paper, okay? So that paper, if you glue both sides, then it becomes like a cylinder. But without doing that, what you can do is, given the band of paper, just don't glue these two sides together, twist the paper and then glue. So in the cylinder form, what happens is, you have this, you glue this side to this side, and you glue this side to this side. It takes the form of a cylinder. But suppose you don't do this, what you do is the following, that you twist and glue this side to this and this side to that. Once you do that, then there is a twist which comes in. Now the problem is, if you start painting one side of the surface, you will end up doing both sides. So let us see why it happens. So suppose I have start painting this side. So I am going on painting this side, I go the other way. Then on the other side, I am painting the other side, but then there is a twist here. So from the outside now I come inside. So I am painting the inside portion now. And then the whole inside also get painted, you see. So that means this surface has got only one side. Since there is a twist on one side of the surface, through that twist you are coming from outside to inside. So there exists only one side. So this is called Mobius strip. For us and for Stokes theorem, this kind of surfaces are bad surfaces. We are not going to deal with this kind of surfaces. We will deal with only those kind of surfaces which has got two sides, two distinct sides, like this picture, like a hat, or let us say dome of a sphere. This has a well-defined two sides with which we can work. Okay, fine. So these are usually called orientable surfaces. But let's not go for those technical terms. Intuitively, all I want to say is we are going to deal with surfaces which has two distinct sides. Okay, and then it would make sense for us to talk about outward unit normal vector. That means I can talk about normal vectors in this direction. Okay, now again I have to talk about the direction of the boundary, because it is involved in Green's theorem also. So suppose this is my surface. So the boundary is this one. This is the boundary of the surface. I demand that the boundary of the surface should be a simple closed curve. On that boundary, suppose I choose the outward unit normal vector in this given direction according to the picture. Then what is the direction on the boundary which we are going to work with? Well, the point is, if I stand here, suppose some person is standing here with his head towards the direction of the outward normal vector, then the surface should be on the left hand side of yours. That is the direction. So according to this picture, the direction is this, because if I am walking in this direction, my head pointing towards the outward normal vector, the surface is on my left. To understand it, let me again draw this same picture. This is my surface. Suppose I choose the normal vector to be inside. So near these points, normal vectors are pointing downward. Suppose some person stands here. Suppose now this guy has his head to the opposite direction of the normal. So that is not the correct way to walk. So the correct way to walk would be this way, that your head is pointing towards the direction of the normal, and then you want to have your surface on the left hand side. That means this is the correct direction. Is this clear now? Look at the first picture. The outward normal is this one. The person is standing here with his head pointing towards the unit normal. Then the correct direction to walk is the direction, so that if you walk in that direction, the surface remains on the left hand side of yours. In that case, the correct direction is this, what I have drawn here. Look at the picture again here. Suppose I choose this normal direction, which is going downwards. So the person walks here with his head downwards, if it is possible to walk. Then the correct direction is such that if you look at the left hand side of yours, the surface is on the left hand side. In that case, the correct direction to walk is this, because if you look at the right hand side of this person with his head downwards, if you look at the right hand side, the surface is not there. Okay? So this is the correct direction to choose. Whenever we try to apply Stokes theorem, for that it will become necessary for us actually to draw the pictures and to understand which way we take the normal, and if we choose one normal, then how do we choose the direction in the boundary. Because you see from this picture, the orientation in the boundary, that means the direction in which I am going to do the line integral, actually depends on the chosen direction of the normal. Okay? Now let us come to the statement of Stokes theorem. Well, before that, let me tell you some thumb rules which we are always going to apply, that how to find the outward unit normal vector for certain given surfaces. Okay? I will tell you just some formulas that will always work for you. So I will just write out some formulas of outward unit normal for you. We will always work with these normals. So a surface can be of the form z equals to fxy, that is one case. Okay. In that case, the outward unit normal vector is given by divided by the norm. So that is 1 plus fx square plus fy square. Okay. Second case is when it's a level set of some nice function g, that is it is of the form g x y z equals to 0. In that case, the formula for the outward unit normal vector is grad g divided by norm grad g. Of course, assuming that this is non-zero, so that it would make sense. Then comes the third case, the parametric form. So if the surface is given by then n is we know how these formulas come. Actually, this last one is the most general, that given the parametric form, what you do is you fix v, then it becomes a curve on the surface, differentiate with respect to the first variable, that gives you tangent in one direction. Then what you do is you fix u, it becomes a curve in the parameter v, that is another curve on the surface, differentiate to get a tangent in the direction, in that direction, take the cross product of these two tangent vectors, that gives you a normal. That normal we are taking as the outward unit normal vector, and then you divide by the norm of that vector to make it a unit normal. Okay. So these are the three formulas which we are going to work with now. Okay, now let's come to the statement of Stokes theorem. So let S be a smooth, I will explain the meaning of all these words, smooth orientable surface bounded by smooth simple closed curve, which we might call delta S. Let f x y z be a vector field such that PQR has continuous first partial derivatives then if delta S is traversed in the positive direction, then we have the following formula: integral over delta S with the proper direction f dot ds. This is a simple line integral. This is equal to double integral over S curl f dot n then d sigma, where d sigma is the surface area of the surface S. So you see the similarity with the Green's theorem. There this double integral over S, that actually was double integral over D, where D was a region in the xy plane, and then the measure we have used the usual, then the area of integration was just dx dy, and the role of n was played by the outward normal k that was towards the z axis in the positive direction. So here, since the surface can be on in some other ways in the space, so instead of k we are going to take the outward unit normal vector. So in Green's theorem, k actually is analog of n. Only extra thing here is d sigma. There the analog was dx dy. Now given any surface S, I can calculate what is d sigma, so there is no problem in that. Now the only technical language here I have used is a smooth orientable surface. There is another smooth here. Well, orientable surface just means, as I said, that you have two well-defined sides, outside and inside. If that is possible, we call the surface is orientable. Okay, it is not, strictly speaking, is correct in the terms of mathematical language, but intuitively it's okay. Orientable means I just have got two sides. You know, I can talk about the outward unit normal and inward unit normal. Now smooth means what? Well, given any surface S, it is either level set of a function, or it is graph of a function, or it is given by some parametric function phi. Well, smooth just means that all these functions has partial derivatives of all orders. It's just a technical condition which I am assuming. So smooth means if it is a level set of a function g, g has partial derivatives of all order. If it is graph of a function f, then f has partial derivatives of all order. Similarly with phi, the parametric function. That is what smooth means. Now to understand the theorem better, what I will now do is, I will take an example, and in case of that example, I will just try to verify Stokes theorem. This theorem is not very difficult to prove. It just uses Green's theorem. You can and change of variable formulas, chain rule, such elementary things. You can look at any standard calculus book for the proof of Stokes theorem. But we are going to assume the Stokes theorem statement, and then I am going to verify it on a particular example and then apply it in certain situations. Okay? So to verify Stokes theorem, let us look at the following example. So first we need the surface. So let S be the part of the cylinder z equals to 1 minus x square. The range of x is, and y lies between minus 2 and 2. Okay. So this is the surface which is given to us, and the function, that is the vector field, let us say that is given by a very symmetric kind of xyi plus yzj plus xzk. Okay. So here first we have to understand what is the outward unit normal and hence the direction of the boundary of that surface. So we try to draw the surface first. So I will draw the surface for you. So this is y axis, this is x axis, let us say this is z axis. Then the surface looks like this. Okay. So the surface is this curved portion. So here obviously the outward unit normal vector is this. Okay. It goes in the top side and hence it is easy to determine what is the direction in the boundary, that is this, then this, then this, this. Because if I am walking in this direction, putting my head towards the normal direction, then the surface is on the left hand side of myself. So the surface is this portion. Okay, this top curved portion is the surface. So first I need to find then what is the expression of normal. So I will use the fact that this is a level surface given by f of x, y, z, that is equals to x square plus z minus 1. Then n, that is grad g, that means twice xi plus k divided by the norm, that is square root of 1 plus 2x whole square, that is 1 plus 4x square. This is the outward normal. You see the positive side appearing in k. Okay. Then the next thing I need is curl f. So I will calculate what is curl f. Then I del x, j del y, k del z, and then xy, yz, zx. If I want to calculate, what do I get? I get I times del y of zx, which is 0 because zx has no y, minus del z of yz, this has 1z, so it is minus y I. Then comes j. With j, I first apply del z on xy, which is 0, then minus del x of zx, which is minus z j. Then k, I first apply del x of yz, which is 0 because it has no x, minus del y of xy, which has 1y, so it is minus xk. Okay. From these two data, I can certainly calculate what is curl f dot n. So curl f dot n. This is the integrand. Since I have the formula of n and I have the formula for curl f, if I do that, what I get is minus twice xy comes from the I component, then j component in n is 0, so it is only the k component which remains, it is then minus x. Okay. So it is minus 2xy minus x. Okay. Then the next thing we need to calculate is the area of integration on the surface. So what I do is, I look at the surface as fxy equals to 1 minus x square. In that case, I know the formula for d sigma is square root of 1 plus fx square plus fy square dx dy. Now this is easy to calculate. It is square root of 1 plus fy is anyway 0 because function has no y in it, it is independent of y. So it is only fx square, but fx is minus 2x, so square is 4x square dx dy. So now I have to calculate the left hand side, that is integral over s curl f dot n d sigma. So this is now, I know the parametrization, that is the variation of x and y. Well, the variation of x is from 0 to 1, variation of y is from minus 2 to 2. Curl f dot n anyway I have calculated, it is minus twice xy minus x divided by 1 plus 4x square. If I go back to previous formula, what happens is, well, this formula is wrong. Curl f dot n is minus 2xy minus x is correct, but one quantity is square root of 1 plus 4x square. Okay, because in n this quantity is sitting. Okay, then in this expression of curl f dot n d sigma double integral over s, I have to multiply with d sigma, but d sigma is square root of 1 plus 4x square and then dx dy. So what I get is integral from 0 to 1, integral from minus 2 to 2, minus x into 1 plus twice y dx dy, which then is minus of, first I do the x integral, that is x square by 2, but limit is from 0 to 1, so I get half, then minus 2 to 2, 1 plus 2y dy, which is minus half into y plus y square from minus 2 to 2. So I get minus half, then 2 plus 4 minus 2 plus 4. Okay. So these two 4's cancel each other. What I get is minus 4 by 2, which is minus 2. So the left hand side in Stokes theorem in this particular case turns out to be minus 2. Now I have to look at the right hand side also. Now before that, let me go to the picture again. What is the boundary curve? That is portion of this two lines which are horizontal and then the curved line, these curves. Okay, so I break it into 4 pieces. The first curve I call C1, second curve, that is this one, I call C2, then the third curve which I call C3, then the fourth curve which I call C4. Okay. Now to do the line integral of the function, I need to know that what do exactly these curves represent. So let me note it here first, that what is C1t. In C1 I notice that x is fixed, z is 0, only y is varying from minus 2 to 2. So we draw the picture again to understand the equations of the curves. This is y, this is x, this is z. So this is C1, this is C2, this is C3, this is C4. Okay. So what is equation of C1? So C1t is x is fixed, it is 1, y is varying, so I call it t, z is 0. This is C1t. Then I have to go to C2t. In C2, y is fixed, it is always equals to 2, only the other one is on the surface, so it is t 2 1 minus t square. Okay. Then C3, which is again like C1, it's a horizontal line, but in C3 what is happening is x is 0, y is varying, and z is 1. Okay, because x is 0 and z satisfies 1 minus x square. So if x is 0, z is 1. So it is 0 t 1. Then comes C4, which is analogous to C2, and that is t minus 2 1 minus t square, because I am on the other side of the y-axis. Okay. Once I know all this, I can calculate primes also. So C1 prime t is 0 1 0, C2 prime t, that is 1 0 minus 2t, C3 prime t, that is 0 1 0, C4 prime t, 1 0 minus 2t. Okay, it is analogous to C2 prime t. Now I need to know what is f of Ct and then integrate in the correct limit. So over C1 when I am integrating, so it is this, over C1, f of Ct dot C prime t dt. So what is the limit of C1? What varies in C1? I see t varies, that is the y coordinate. And how does it vary? Well, before going into that calculation, let us first check what is f of Ct into C prime t. Okay. So what is f of Ct? F is x into y plus then y into z, then z into x. Okay. So this is then, it is t, that is xy, yz is 0, then zx is also 0, dot C1 prime t, that is 0 1 0 dt with some limit, but that limit I don't need to calculate because I see the dot product inside is already 0. So I get that this is 0 without even calculating the limit. Now I have to go to C2, that is f of C2t dot C2 prime t dt. Now I need to know what is the limit of integration. Well, here it is very easy. In C2 the variation is only of x and it is varying from 1 to 0. Okay. So this variation is from 1 to 0. See, that depends on the chosen direction. I am going in this direction. So here x is 1 and here it is 0. So it is going from 1 to 0. So let us calculate what is f of C2t, that is 2t, that is xy, then yz, that is 2 into 1 minus t square, then zx, that is t into 1 minus t square, times, now the dot product of C2 prime t, that is 1 0 minus 2t dt. If I calculate this, what I will get is, the second portion goes away because there is 1 0, so it's 2t times minus 14 to 1 minus t square. Okay. So this is then equals to integral 1 to 0 2t into, let us check, it is the product of this quantity into this quantity, that is minus 2t square into 1 minus t square. So this is minus 2t square into 1 minus t square dt. Okay. Now this integration can be easily calculated, and if you calculate this I leave as an exercise, that it will turn out to be minus 11 by 15. Check this. Okay. Then C2 has been taken care of. I have to now go through C3. So what is f of C3? I know the formula of C3. This is 0t1. So I have to calculate what is f of 0t1. This is xy, which is 0, then yz, then zx, that is again 0. So integral over C3 in this direction, f dot ds I have to look at. This is integral. Then I have to see what is the limit of C3. C3 varies from this way to this way. So this is from 2 to minus 2. It is from 2 to minus 2. F of Ct, that is 0t0 dot, now I need C3 prime t. So this is C3 prime t, 0 1 0. So it is 0 1 0, then dt. So this is integral 2 to minus 2 t dt. This is an odd function whose integral I am doing from 2 to minus 2. So this integral certainly is 0. You can also calculate it, it is t square by 2. So half comes out. So 2 to minus 2 t square, which is 4 minus 4, that is 0. So C1 does not contribute anything, I got 0. C3 does not contribute anything, I got 0. Only integral over C2 came out to be minus 11 by 15. Now I have to calculate what is f of C4. That is f of, what is the equation of C4t? This is t minus 2 1 minus t square. So t minus 2 1 minus t square. I can calculate from the formula of f. So it is xy, then yz, then zx. Now I need C4 prime t, whose formula I know, I have calculated it once. It is 1 0 minus 2t. So this is 1 0 minus 2t. This implies I can calculate f of C4t dot C4 prime t. That turns out to be minus 2t, then minus 2t square into 1 minus t square. Okay. Now I have to integrate. To integrate, I need to know the limit of t. Since it comes this way, the variation of t, that means of x, is actually from 1 to 0. Okay. So this last integral, integral over C4 f dot ds, this is integral from 1 to 0. Let us look at it again. X varies from here to here. This anyway I know is 1, this length is 1 as I have written here, and this is 0. So the variation of x in this case is the reverse of C2. You know, in case of C2 it was varying from 1 to 0. In case of C4 it will vary from 0 to 1. So what I will get is integral from 0 to 1 minus 2t minus 2t square into 1 minus t square, then dt. This integral is also easy to calculate, and if you do this, you will get that this is minus 19 by 15. So finally, when I look at the total line integral, that means integral over C f dot ds, I write it as integral over C1 f dot ds plus integral over C2 f dot ds plus integral over C3 f dot ds plus integral over C4 f dot ds. Now this integral is 0, C1 that we have seen, this is also 0, this turns out to be minus 11 by 15, and this turns out to be, well, C3 turns out to be 0, C4 turns out to be minus 19 by 15. If I add these two, what I get is this plus this, I get minus 30 by 15, which is equals to minus 2. So the line integral portion turns out to be minus 2, but if I look at the surface integral portion, which I have earlier calculated, that also turns out to be minus 2. Okay? So that means curl f dot n d sigma double integral over s is turning out to be the line integral of the function over the curve C. But note that for this, it was really important to choose the direction properly. If in the picture I had chosen the direction this way, you can check yourself very easily that the integral will actually turn out to be equals to 2, not minus 2, which it should be. So if you want to choose this direction, you have to choose the downward unit normal vector. In that case, the surface integral will turn out to be equals to 2, and then they are same. So check it yourself. The exercise is the normal which I have taken, take the normal, same normal but with a minus sign. That means the direction of the normal is reversed, and then change the directions of C1, C2, C3, C4 in the opposite direction. Then you will get that those two integrals are same. So what does it say? It says exactly what I said about the choosing the direction of the boundary curve, that you choose it in such a way that if your head is towards the normal, then the surface should be on the left hand side of yours. With that convention, we have verified Stokes theorem. So these lectures were about connecting the double integral with line integrals. In the next lecture, we will go to something called divergence theorem that will connect triple integrals with surface integrals. So that is going to be the last generalization of the second fundamental theorem of calculus, which we are going to deal with. So in the next lecture, we will start with triple integrals and surface integrals.